Okay, and I will switch to silent mode from Skype. Okay. Of course, you can ask the questions along the presentation, so interrupt me anytime you want to understand anything, or you will need some more additional comments. Question number one to you. How familiar are you with the membrane pumps?
I only know there are some kinds like a rotary vacuum pump, oil pump, cryo pump, diffusion pump.
Okay, I see. So in this presentation, we will talk about the two types of the pumps, membrane pumps and the rotary vane pumps, which are also called the oil-sealed pumps, due to the fact that the sealing is done by the oil in those pumps. There are definitely there are other types of the pumps, and one of them was actually I've sent you the pictures of the molecular of the short path evaporator that we installed in the beginning of this year, together with the how is it called, the diffusion pump? Yeah, diffusion pump. But this is for a very high vacuum application. Well, not very high, for high vacuum application, medium or high. I will show it to you in a minute, the separation that is marked. But for the applications that takes that we can have with Asahi products, two main types of the pumps would be, first of all, membrane pumps, and the second application would be for the rotary vane pumps. There is also some space for the scroll pumps, which are dry chemical pumps and are manufactured by different manufacturers like Edwards or Anestevata or Pfeiffer labeled, but they are pretty specific, and again, mainly for the Asahi products, two main types of pumps would be membrane pumps and rotary vane pumps. Well, this slide shows that the first actually vacuum pump was invented like in 1650, so it is roughly 350 years back. Although it was pretty simple one, still it was pretty effective to pump out the water out of the earth. Vacuum brand is one of the main, I think, or even the main manufacturer. I'm not quite sure about the figures, but I definitely this is one of the main players on the market in terms of the manufacturing the membrane pumps and oil sealed pumps or rotary vane pumps. So the first one was introduced to the market in that's the picture of the two-stage rotary vane pump. So what you can see here on the right side, that's the drive, and these two cylinders are the stages. So that's the first stage and the second stage of the rotary vane pump. Vacuum brand, actually, I don't know if you know that vacuum brand is the used to be a, well, I'm not sure if it was used to be, but it was born by a company called Brand, which is the manufacturer of glass items like pipettes or flasks. And they also manufacture some dosing items. But so that is why it is called Vacuum Brand. They are even located on the same road, just on the opposite of each other. Both, of course, companies are located in Germany. So now that's the slide of for the vacuum. I've made some translation for this time. So rough vacuum, what is called the rough vacuum, is the vacuum that goes from 1000 millibars, so from 1 bar down to 1 millibar. Medium vacuum is what is called the vacuum that is in the range of 1 millibar down to 1 to the 3 millibar. How to say that, 10 to the 3 millibar. Yeah. So high vacuum is 10 to the minus 3, from 10 to the minus 3 up to 10 to the minus 7 millibars. and ultra high is 10 to the minus 7 up down to 10 to the minus 12. In terms of definitions, it is important to keep in mind that that we should properly say that we have the high vacuum, which means that the pressure is very low, because there are some people who mix these kind of things. So they say that we have a low vacuum. Low vacuum means a high pressure. So if we are talking about the vacuum, rough vacuum is the low vacuum. What vacuum pump manufactures is the membrane pumps, as I mentioned already, and rotary vane pumps. These figures, this one is slightly outdated. Now they have bigger machines, which are actually the combination of the biggest membrane pump, but they can go up to, as far as I remember, 48 cubic meters, maybe even higher. I'm not quite sure. This can be seen on their webpage. Welsh vacuum, which I mentioned already to you, it used to be called Ilmvac. Now it is called Welsh Vacuum, and it is a part of Gardner Denver Group. They are also manufacturing the membrane and rotary vane pumps. And there is a third manufacturer, which is called KNF, also a German manufacturer. They are manufacturing only membrane pumps, but they are also manufacturing compressors. So in case you need a compressor for some application, maybe, then you can take a look at their product range as well. The product range of the membrane pumps by KNF is pretty small. So for me, in terms of the membrane pumps, number one is well, I'm not quite sure which company is number one, but two main companies that I consider as the manufacturers are the Vacubrand and the Welsh Vacuum. Let's skip this one. So this is the following slides would be about the typical applications. These ones are in Russian, but I will quickly translate to you what it says. Well, first type of the application is a very typical one, is the filtration. And when we're talking about the filtration in terms of the Asahi products, definitely we are, first of all, at least for me, we're talking about the filter reactors and Nuch filters. By the way, regarding the terminology, I'm not quite sure if we discussed that with you, but I decided personally that in Russian market we will call them a Druk filter, because what is usually called a Nuch filter is the filter that works under vacuum. And the great advantage of Asahi product is that you can use not only under vacuum in the Nuch filter, but you can also work under pressure, which is great. And there are not too many manufacturers who can offer this kind of option. So when we're talking about the filtration, there are some main demands for the vacuum pump. So first of all, that's the point number one. It should be resistant to chemical aggressive compounds, vapors, because we are pumping out something. I mean, we are pumping out the air, but it also will has some vapors of the substance that we have in the receiving flask, for example. In case of the filtration, we do not need a very high vacuum, because the main idea of the filtration is to create a maximum pressure drop. So for the filtration, 80 millibar is more than enough. And because we already will have, in terms of the filtration under vacuum, we'll have a pressure drop of almost 1 bar, 920 millibars to be precise. And there is no need to create a higher vacuum, like 20 millibars or 5 or 1 millibar, because it won't give us too much additional force in terms of the pressure. We also need some protection for the pump in order to avoid the droplets or solid particles to how to say that, to get into the pump, because this can damage the membrane or the vacuum valves that are inside of the pump. And we definitely need the vacuum control system. In case of the filtration, this can be a manual one. And why do we need it? We need it because when we're filtering some low boiling solvent like I don't know, ethanol or ether or whatever. In case we will have a pump that can go down to 80 millibars, definitely the solvent will start to boil, and this is not good because all the vapors will go into the pump and will collect on the outlet of the pump. Second application, again, a very typical one, and again, this is something that you manufacture. Well, I mean, not this one, not these units, but you manufacture the rotary the rotary evaporators. So, what kind of the request we have in this case for the vacuum pump? We first of all, definitely, we need a chemical resistant pump. It is important for the same reason as for the filtration, because we have the vapors of different kind of solvents or substances. We need a relatively high vacuum. So in this case, most of the customers are pretty fine with a vacuum down to 2 millibars. But in the reality, what the customer, this is kind of a step forward, but it is very important to understand that even if you buy a pump which can go down to, let's say, 7 millibars, it makes no sense. Well, it is not even to makes no sense. You will not be able to go down to 7 millibar in case you are evaporating, for example, ethanol. Why? Because when we start to increase the vacuum level, so we are decreasing the pressure. In this case, when the ethanol starts to evaporate, and it starts, let's say, that depends, of course, on the temperature in the bath, but let's say this can also be seen in the in tables and so on. But for example, if it starts to boil at 500 millibars with a temperature of, I don't know, maybe 50 degrees Celsius in the bath, then you will not be able to reach a higher vacuum until all the ethanol will evaporate from the evaporating flask and will collect in the receiving flask. Why? Because we have the vapors. So when the vapors starts to appear here, so the boiling process starts, then we have the vapors. Although the pump continues to pump, it will just create an additional force for the vapors to evaporate from the evaporating flask and condense on the condenser. They will fly from the evaporating flask to the condenser and will condense and collect in the receiving flask. The other portion of the vapors is on the go again and again. So there is no need to have a very high vacuum pump for the rotary evaporator. And another, of course, point is there are some customers who say, I need a vacuum pump that can go down for the rotary evaporation. I need a pump that can go down to the, I don't know, 0.01 millibar. Again, it makes no sense for this such a high vacuum pump, because most of the rotary evaporators are not designed to work at such a high vacuum due to the leaks which are in the system. So, for example, for the small rotary evaporators from Haidel, Buchi, Aika, typical vacuum, maximum, not a typical, the highest vacuum they can operate at is 1 millibar. For the higher vacuum application, they are not designed for a higher vacuum application. Any questions? No?
No. Yes, fine.
Okay, clear. Just in case you know something, just let me know and I will skip that slide and I will continue. So, so not to take too much of your time. So, of course, in this case, we need the vacuum regulation, vacuum control, in order to do the evaporation at a certain vacuum, not to overboil the substance. And, of course, we need the regeneration of the solvent. Because we want to collect the, for example, ethanol that we evaporated from the evaporating flask. There is another application that's the how do they call it, the rotary vacuum centrifuges. It is the idea for the main goal. for this application is the same as for the rotary evaporator, but the translation from Russian into English takes some time. But the technology is different. So in this case, the customer has their substance in these tubes inside the centrifuge, and they start to apply the vacuum, and the substance won't boil off the tube due to the centrifugal force, because when we start to, first of all, we start to rotate, and then we start to apply the vacuum. So this is another type of the application. Same requests as for the rotary evaporators. Why do we need why do we need this kind of application? The limit of the rotary evaporator is the amount of the tubes or flasks that we can have to be evaporated simultaneously. So as far as I know, the maximum amount of glass tubes that we can have in the rotary evaporator is something like 20 with a volume of about 10 to 20 milliliters. In the centrifuge, we can evaporate simultaneously a huge amount of samples. And on the picture that you can see here is the tube with a volume of 50 milliliters, and you can definitely, it can be definitely seen that there is much more than 20 units, 20 tubes can be put inside the centrifuge. And if we are talking about the small tubes like, you know, Eppendorf with a volume of, I don't know, 2 milliliters maybe, you can easily evaporate simultaneously a very huge amount of the tubes. That is why we have the this kind of machines. Fourth application is the vacuum drying chambers, vacuum drying ovens. Requests are pretty much the same as for the rotary evaporator, except for the vacuum level that we need. In this case, we can go as we do not have any rotation, like, you know, here in the rotary evaporator, so we can go to a higher pressure, because we do not need, you know, a special design seal. Everything is static. So we can go down to 10 to the minus 3 millibars, and thanks to that we can reach a higher level of dryness, and that is why we need a higher vacuum pump. In some cases, for this kind of application, we may also need an explosion proof as well. Actually, for the rotary evaporators, it is not marked here, but in some cases we need an explosion proof pump. This type of the application I am not familiar with at all, but this slide says that we may need a vacuum pump for drying the gels. That's some kind of a biological application, and I've never met any customer who is doing this kind of stuff, but not because there are not too many customers out there, just because we are working in the other field. We are mainly working with the pharmaceutical and the food industry, and this kind of application is more for biological industry. Sixth application is the freeze dryer, and it says freeze dry and short path evaporation or molecular distillation. In this case, we again need a high vacuum pump, which can go down to 10 to the 3 millibars. We need a high pumping speed. We need a chemical resistance, of course, and we need a protection from the condensate. This is an important point, and the Vacuum brand, as well as Welsh, they have a very interesting, they call it hybrid pump. I will explain to you later on in the presentation what it is. Seventh application, I think there is, not the last one, but nevertheless. Seventh application is the creation of the vacuolan. The vacuolan is the definition that is used by the, I think they even made it a trademark or something, by Vacuum brand. And in this case, we can have only one pump in the laboratory. that can create vacuum for different working places. Like you can see here on the slide, it has the vacuum controller here. It has an additional vacuum valve here and here on the table as well. Again, I will talk about it later on in the presentation. Same requests for pretty much the same requests for the vacuum pump. So we need a relatively high vacuum that can go down to the, let's say, 1.5 to 7 millibars, high pumping speed. This is pretty obvious because we have a lot of well, not a lot of, but anyway, more than one applications that will require the vacuum. That's why we need a high pumping speed. Definitely we need a chemical resistance. We need some protection for the pump. We need the regenerator for the vapors that will go anyway, will get into the vacuum pump. And there is another request, which is point number 6, switching on the pump only when the vacuum is needed. This will allow us to save some energy, and that is important. Yeah, that's the the last application that is mentioned here is the four vacuum pump for different kind of applications. Like, for example, in that application for the short path evaporator, when we are using diffusion pump, we had a 4 vacuum pump which was used to create the relatively low vacuum, rough vacuum, so we can start the diffusion pump. Or in this case, on the picture, you can see at the back side there is a membrane pump that is used as the 4 vacuum, and the turbomolecular pump, which is here. Why do we need it? Both turbomolecular pumps and diffusion pumps, and any kind of high vacuum application requires this kind of a 4 vacuum. Why? Because in case for different reasons, for different type of the pumps, but let's say for the turbomolecular pumps, we can switch it on, but due to the high amount of the air, of the gas, not always the air, but any kind of gas that it has to pump, due to high amount of gas, it will hit the pump, the turbine will heat up very quickly because the throughput of the pump is very, very high due to the performance, the speed, the rotating speed, and so on. And as soon as it will heat up, it will switch off automatically. Otherwise, it can be broken. It can break. Is it clear?
Yes.
Okay. In terms of the diffusion pump, which is another type of the oil pump, in that case, a high amount of air is not permitted due to the fact that the oil which is inside of the diffusion pump may start to burn. That is why we need a 4 vacuum pump for the diffusion pump. Now going further to the description of the pumps. So we'll start with the membrane pump, as this is one of the main type of the pumps that is used with the reaction systems or manufactured by Asahi or any other manufacturer. So how does it work? Actually, it is a pretty simple item. It works in the following way. So here on the right side we have the inlet, on the left side we have the outlet. That's the eccentric that moves up and down due to the drive, which is here on this axis, and this is the membrane. So here we have the vacuum valve. I'm not sure, can you see that it moves, slightly moves down, and this one slightly moves up?
Yes, I can see.
Okay, so the thing actually is pretty simple. So when the membrane goes down, this valve opens, and this valve is actually, it cannot move down because it is located on the other side of the chamber. So when the membrane goes down, it only sticks even more tight to this how to say that, this part of the vacuum chamber. And when the membrane goes up, then everything occurs the other way around. So this valve sticks to this part, and this valve opens. Is it clear?
Yes, yes.
Perfect. In terms of the types of the PAMPs, there are different ways of how we can connect the vacuum chambers. We can connect them in parallel, or we can connect them one by one. In case we connect them in parallel to the system, like here we can have the so-called that's the one-stage pump. We connect them in parallel, so we have you can see here the picture. The blue one shows the one-stage pump. It gives the maximum performance but a very low vacuum. In terms of the names, it is pretty common thing for Welsh and for vacuum brands, so they have, so once you understand it, you can easily determine what kind of pump we're talking about. So for the vacuum brand, M stands for the membrane, E stands for ein, which is in German means one. Zwei, that's the zwei, drei, and vier, which stands for the amount of the stages. So if we're talking about the ME, this means that's the membrane pump, one-stage membrane pump. That's the two-stage and three and four stages membrane pump. So as I told you already, in case of one-stage pump, we have the maximum performance, but a very rough vacuum. We can also connect the chambers one by one. So in this case, we have four chambers, but each of two are connected one by one, and this allows us to reach a higher vacuum. In case of the three stages pump, we can reach a even higher vacuum. In case of four-stage pump, we can reach up to 0.5 millibars. They made the vacuum brand and the others made some investigations. They tried to create a five-stage pump, but due to the physical limitation, it doesn't give any additional advantages in terms of the vacuum that can be reached. So they stop on the four-stage pumps. What is also very important to keep in mind, and this is something that surprisingly to me, most of the customers do not understand, that it is important not only to have a high vacuum, but you need always to consider the performance of the pump at the vacuum you are going to work at. So what does it mean? You can see here on the graph the performance of the pump. Here on the y-axis you can see the performance, and here you can see the pressure. When you are measuring the when you are reaching a maximum highest vacuum that the pump can reach, it gives you a zero performance, which means that it will not pump anything at all from the system. So for example, if you have in a system the leak rate of, I don't know, let's say 0.1 cubic meter per hour, then it will never reach a vacuum of, if we're talking about, for example, this four-stage pump, it will never reach a vacuum of 0.5 millibar. Why? Because it has a zero performance at 0.5 millibar. Is that clear?
Oh, I'm sorry, I didn't get it.
Okay, let me explain it once again. So, for example, you are Very simple example. Let's imagine you are decided you are a Superman and you decided to breathe in all the air from the atmosphere. Definitely you will never be able to do that because there is a huge amount of air in the atmosphere, you know. In order to breathe all the air inside of you, you need to be really to be a Superman and have lungs with the size of the atmosphere. Yep. So pretty much the same with a vacuum pump. If you have a leak rate in the system, which is, let's say, 0.1 cubic meter, you see, is it clear? Yeah, what I'm talking about. And the pump has the performance of 0.1 cubic meter as well, then the forces will be equalized. So you are pumping out 0.1 cubic meter, but due to the leaks, you always have the same amount of air that goes inside the system. So you will, even if you are, let's say, you have, let's imagine you have a pump, you have a system with a leak rate of 0.1 cubic meter. In case of a leak rate of 0.1 cubic meter, there should be a relatively high, hole in the system. So you have a pump with the same performance as the leak rate. So although you are pumping out something out of the system, the same amount of air at the same time goes inside the system. So the system will never have any vacuum in it at all. Clear? So, sure. Is it really clear? I can explain it once again.
I think I got it. Yes.
Okay, perfect. Then let's imagine you have a pump with a performance of the let's imagine 1 cubic meter per hour and the leak rate of 0.1 cubic meter. Then definitely you will be able to create a certain vacuum inside the system because the performance of the pump is higher than the leak rate. So this is why it is very important always to keep in mind that you need to take a look at the performance rate of a certain vacuum. So when we're talking about the application which requires, I don't know, maybe 1 millibar, because that's the vacuum when your substance starts to boil. You will definitely need a pump that can go not only below 1 millibar or down to 1 millibar, but it should also have a relatively high performance at this vacuum. Because if you have an application which requires 1 millibar and you buy a pump that can go down to 1 millibar, you will never reach 1 millibar because there is always a leak inside the system. Always. Unless you have an extra super duper highly sealed system. This kind of system exists as well, by the way, but they have another type of the leaks. Not the leaks from the atmosphere, but the leaks from the surface of the materials that this chamber is manufactured of. Another type of very crazy leaks, but this is not something I wanna kill your brains with, because this is the high vacuum applications, and this is not something that you are dealing with in your daily business. That's mainly for those who are selling adverts for vacuum pump, high vacuum pumps, or labeled or FIFA, like turbomolecular or ion pumps, to imitate the space. These kind of things are very interested for these applications, or for example for nuclear bombing. Not talking about the nuclear bombs, I mean the particle accelerators, like the one which is in Switzerland, a huge circle, forgot how they call it, the collider. Yeah. So summarizing all what I said, it is very important to keep in mind that when you are talking about the vacuum application, you need to choose the pump that will have a certain performance at the vacuum that you are going to work at. So, for example, if we are talking about the three-stage pump, I'm not sure if you can see those small marks here on the screen, but they are here. So I would say that if you're buying an MD pump, three-stage pump, which can go down to 1 millibar, I would say that you will be able, in terms of in case of the rotary evaporator, you will be able to reach the vacuum of, let's say, about 3 millibars. So here we have 1, 2, and 3. 3 millibars is pretty much okay. So for this, that is relatively possible. Why? Because we have a leak rate. Main leaks occurs in the seal that seals the vapor tube, but there are also other leaks that we can have in the system, like on the flanges or on the joints and so on. Okay, clear?
Yes.
Perfect. This is the design of the standard vacuum pump. I think about two.
Sorry.
Yep.
Can we come back to the previous slide?
Yeah, of course.
So the green, red, blue shows different graph. Is this, for example, green represent MD?
Yep.
Ah, okay.
Yeah, blue for the one stage, red for the two stages, green for the three stages, and purple for the four stages pump.
Ah, okay. Got it. Thank you.
So that is why actually we have the lower performance but a higher vacuum, because in the one stage pump all the chambers are pumping out simultaneously, and so you can pump out more gas at the same time. But in case we have a two-stage pump, the second stage works as the four vacuum pump. So it creates a so-called four vacuum, slight vacuum that allows, how to say that, ease the work of the first stage. That is why it can go down to 7 millibar for the two-stage pump. I'm not quite sure if I'm possible if I can at the moment explain it properly in English. So this is something that I need to prepare for. But if you are interested in that, I think I will summarize that in a short letter, and that as we already discussed the design of the chamber and how it works, I think it will be pretty easy to understand. But in general, you need just to keep in mind that in case of one stage, you can go down to roughly 100 to 70 millibar, depending on the design of the chamber, and so on.
So usually for the reactor system, so two-stage would be enough for most of the applications.
Again, that depends on the application. But I would say that in 80% of the application, two-stage is more than enough. There are, let's say, 20% of the other application, and I would say that again, according to my experience, maybe 15% will require a three-stage pump, and other 5% may require a higher vacuum. But again, that is important to define what we call the reaction systems, because if we're talking about the reactors, then just as I said, the separation won't be as I said. But if we're talking about the Asahi products in general, then definitely there are higher vacuum applications, like short path evaporating, and as well as for the rectification column, because we are using rectification column not only for low boiling substance to separate the low boiling substance, but also for high boiling ones, like in this case for Azot customer. But in general, yes, you are right. Most of the applications would be satisfied with a vacuum pump that can go down to 7 millibars. In general, in most of the cases, it is more than okay.
So the one you are talking, Welch vacuum pump, the is it two stage?
This is not a membrane pump. This is the rotary vane pump. We will talk about the rotary vane pumps later on. I'm not quite sure at the moment which one I will offer to the customer. This is something that I need to discuss with the customer, because actually the customer sent us well, very specific customer. Let's say so. He already confirmed that he's satisfied with the reactor and with the filter that we offered. We are now discussing the rectification column, and although in the beginning he asked for a glass column, later on he said that I would be quite fine with a steel column or maybe titanium, or any kind of metal. Well, not actually any kind of metal, because he, as far as I understood, he has some hydrochlorine. So this is quite a tricky thing when we're talking about the metals, because definitely that wouldn't be a stainless steel, because it will corrode. And so I'm now thinking of the arguments to push him to agree on the glass column, and to make him to purchase the vacuum pump as well. So this is, the combination of actions. That is why I've asked you about the maximum vacuum level, because in the quotation it was mentioned that the maximum level is roughly 2 millibars, so 2.6 pascals. 0.6 yeah, no, 266 pascals. Yeah. So this is somewhere on the border. That is why I've asked about 0.1 millibar, which would be definitely fine. And in this case, we can offer a rotary vane pump. 0.1 millibar is not an application for the membrane pump, because we will not be able to reach such a high vacuum with a membrane pump.
Okay.
So
I see.
Yeah, combination of actions.
Okay.
Can we move forward?
Sure.
Okay, so this is a typical design of the vacuum pump. Well, not really typical, because that's quite a special type of the pump. But let me quickly explain to you what we can see here. So here is the vacuum controller. That's the old one, actually, because this presentation, I think, is from 2010. When this controller was pretty new one. Now they have the controller which is called CVC Pro, as far as I remember. The idea is, I mean, what we can do with the controller is still the same. They just redesigned it, and they made a touch screen instead of the buttons, and it became a color one. My personal how to say that, not a feeling, preference. Yeah, my personal preference is to avoid any kind of sensor touch screens in the lab. Why? Because my background is organic chemistry, and I know how the chemists works in the lab. They have a dirty hands. They pretty often wear gloves, not only rubber ones, which are relatively thin, but from time to time we put the tissue glove. Tissue, is that the right word? You know what I mean? Yep.
Yes.
Yeah, and we put the rubber gloves on the tissue gloves. So in this case, we have a relatively thick layer of gloves on our hands, and in this case, the sensor screen may not work. That is why I'm always very careful with touch screens. Of course, you may have a stylus, but you need to have the stylus near the vacuum pump, or I don't know, for example, thermostat. And stylus is something that you will always lose because that's the lab. Yeah, you know. So that is why I personally prefer to have the machine that will have the manual control, well, how to say it, not a touchscreen controller, but a button controller. That is why I like that Welsh still didn't switch to a sensor, touchscreen controller. But that of course depends on the type of the touch screen and so on. But that's the question of buts and the question of what if I will have a thick glove, how thick the glove can be, and will I still be able to operate if I will have the glove with the thickness, will I operate the controller, touchscreen controller, if the thickness of the glove is 1 millimeter, 2 millimeters. I don't, because we can have such a thick glove on our hands in the lab. So I'm pretty sure that if you will talk to the guys, to your guys from the production, as far as I saw, they all wear pretty thick gloves, and if they have the, well, I don't know, gas burner with a touchscreen controller, that would be a problem for them.
Yeah.
So that is the point you should always have in mind. So going back to the what we can see here on the slide. So that's the controller. This is the vacuum pump itself. It can be easily seen that this is the four chambers pump, the pump that has 4 chambers. Why? Because the chamber is a square one, because the membrane is a circle. And you can see here that you can have one. You have you have one chamber here, one chamber here, and 2 chambers at the other side. It is not obvious from the picture how they are connected to each other. So going back to this slide, we can have 4 chambers. The 4 chambers can be connected in a different way, in different ways. But you can definitely say that it has 4 chambers. The thing at the bottom is the drive that rotates this mechanism. Here we have that's the quite a special, I would say, vacuum pump that I personally never sold, and I'm not quite sure if there are many ones around. But this is the pump that can control simultaneously 2 different applications, which is pretty unusual. But the advantage of this kind of pump is that it can, first of all, it can save space, it can save some energy, and it can save some money, because to buy 2 separate pumps is more expensive, definitely, than to buy one pump with the 2 controllers. So here at the top we can see the manual controller. Here at the bottom, for the second application, we have the automated controller, that's the vacuum valve, and the controller that controls the vacuum valve. Here at the bottom we have the receiver for the solid particles that can fly from the application, and this is the protector. This is a receiver that is used as a protector for the pump. So once some solid particles will get into the vacuum line, into the tube, the solid particle will just drop onto the bottom of the flask, and will not go into the vacuum pump. It is important to have such a protector. Why? Because the vacuum chamber is manufactured from the PTFE, from Teflon. And as you know, Teflon is pretty soft material, and it can be easily damaged. Once it will be damaged, you will have to replace the membrane, at least the membrane of vacuum valve. And here we have the outlet of the pump. There is a condenser here and the receiver for the condensate that will condense. Why? It is important again, this is something that I personally thought this is the kind of cheating and lying to the customer. This is something that the customer doesn't need at all. But no, I was wrong. This is the receiver. When we have the vapors from the application that go into the pump, and they will always go into the pump. Why? Because when we start to evaporate something, we will never be able to control the vacuum so precisely that we will avoid the well, no, let's explain it the other way around. When we have for example, let's go back to a picture. We have the rotary evaporator. Yep. If the chiller that we choose is not powerful enough to condensate all the vapors, the certain amount of vapors will go into the vacuum pump. And I can tell you that in 100% of the applications, we will definitely have some problems with cooling. Why? Well, first of all, of course, the customer maybe chose the wrong chiller, or maybe they have a very high temperature of the cooling liquid in their central cooling system, or maybe we applied too high vacuum, or maybe we heated up the evaporating flask too high, and so on and so forth. So there will be always a certain amount of vapors that will go from the application into the vacuum chamber. Once inside the system, we always have a vacuum. But once the vapor goes out of the pump, it goes out to an atmospheric pressure. And the vapor will always, of course, condense, well, not always, but 99% of the vapors that goes out of the vacuum pump will definitely condensate. And it will be collected here in the receiver, which is located on the outlet of the vacuum pump. Did I explain that clearly?
Yes, that too much vapor coming from the, for example, reactor. It needs to be condensed, and then it goes down to the receiver, so that the vacuum pump control the vacuum level more precisely.
Yes, we need to control it more precisely, but in case we didn't do it properly, there will be always a certain amount of vapors that will go through the vacuum pump and will fly out of the vacuum pump. And as they are flying out at the atmospheric pressure, they will immediately condensate. And if we will not have this receiver here on the outlet of the vacuum pump, the vapors will condensate and there will be a big amount of, how to say that? Oh, I know that word in Russian. Let me check the vocabulary. I will maybe remember then this word. Puddle. Yeah. Pool of condensated solvent under the vacuum pump. I can give you one good example. When that was when I learned that this is a very important, how to say that, important option for the vacuum pump. I sold, that was back in 2010 when I sold two 20 liters rotary evaporators to the customer, and they were evaporating THF solvent, which boils at about 64 Celsius, plus 64. We were evaporating the amount of, I think, about 6 liters of during the test runs of the rotary evaporator after the installation. And when we evaporated 6 liters of THF, we collected about 200 milliliters of THF in this receiver. So imagine you have the puddle of 200 milliliters of THF under the vacuum pump. Definitely, this is not something that you want to have in your lab. First of all, because it is an explosive proof, explosive solvent. Yeah, it is flammable one, so it is very important to have this kind of additional protection for yourself safety.
Okay, I got it.
Okay, moving forward, Vacubrand also has some explosion-proof pumps. They here again, as I said, this is an old one, the old presentation, but they have bigger models now. They have 3 models, which are MZ2, MD, or yeah, I'm not quite sure. I think anyway, with a performance of 2, 4, and 8 cubic meters per hour. What is the difference between this pump and this one? All of the pumps by Vacubrand and Welch are certified to pump out the explosive vapors. But they are certified to pump out the explosive vapors. Well, not all chemical resistant pumps, but they are certified to pump out the explosive vapors that are inside the vacuum chambers, so inside the pump. So you can pump out the explosive vapors, but you cannot put the pump inside the explosion, yeah, how to say that, EX zone. Yep. So what you can do, you can have your tube which goes from the applications through the wall to a safe area where you have the vacuum pump, and you can have another tube which is connecting, which goes from the outlet of the pump back to the explosion-proof area, explosive area.
Okay.
So in this case, you have the pump which is located in a safe area, but the vapors that are pumped by the pump, they go into the pump, which is internally has an internal explosion protection, and they are going out of the pump back to the explosive area. Like pretty similar with like with the thermostatic equipment. So when you have the thermostat that is non-explosion proof, you put it behind the wall. Yeah, and you have the tubes that goes out inside the thermostat and back to the reactor. Same idea.
Okay.
Clear?
Clear.
Okay, perfect. But in some cases, you will need to put the pump inside the explosive area. And in this case, both Vacubrand and Welch, they have solutions for that. They have completely explosion-proof pumps. As you can see here, they like standard vacuum pump has the PTFE tube, just a PTFE. And in case of the explosion-proof pumps, you can clearly see that it has the black tubes. Why? Because that's the carbon-filled PTFE to get rid of the static electricity. There are also some additional protections, like this how to say that, this cover or whatever you call it, so on and so forth. So this is an important thing to keep in mind. So in case you need it, the explosion-proof pump, membrane pump, they have it. Here is the protection class. You can see here that they can manufacture. So I'm not sure if I don't know if you're familiar with the protection classes, but in most cases, first of all, you need to take a look at the temperature protection class. So once you have the T3 protection, okay, this time won't go deep into the ATEX protection. Just keep in mind that they have this kind of models. If you will have some question, just let me know. I will explain to you more about this. Because explosion protection is a very specific theme, and it requires an additional training.
Yes.
Now, besides, you have another standards in Japan, unlike
Yes.
we have in Europe. So I'm not sure if that will be a useful information for you. Okay, type of the controller that we can have inside the pump to control the vacuum. There are three types of the vacuum control that we can have. The most simple one is the manual one. You can see here vacuum station with a manual controller and dial gauge. Very simple one. Second type is the valve control. So we have here the valve which opens and closes. So you can see here already a digital controller, unlike here we have the manual one. So you can set a certain vacuum, and at the start moment the valve is open, so the pump works. The pump itself works continuously, and as soon as the controller, which has the vacuum gauge inside the controller, detects that the vacuum that was set is reached, the valve closes. Once the controller sees that the vacuum starts to decrease, so the pressure starts to increase, it opens the valve again, and as soon as the pump continues to work, the vacuum inside the system starts to reach the desired vacuum, which was set on the controller. Clear? Perfect. And there is a third type of the vacuum controlling, the most advanced one and the most precise one. I will explain to you about it more in details on the next slides. This is the controlling system, the system that controls not the valve. You can see here that we do not have any valve here, but it controls the speed of the drive of the pump. Now let's explain what is the manual. With the manual control system, everything is pretty simple. You need always to take a look at the gauge. You always need to rotate the valve, the knob, in order to control the vacuum. But of course, most of the customers do not want to. I call it do not want to hypnotize the controller. They just want to set the vacuum and go and do some other stuff. So most of the customers prefer to have this kind of controllers. This kind of control is perfect for the filtration, by the way, but for distillation, definitely we need an automated control system. So what is the disadvantage of the well, let's start with the advantage. The advantage of the valve control system is the price. So it is relatively cheap. But there is a big disadvantage for this kind of vacuum controlling, which is the hysteresis. I'm not sure if I'm pronouncing the word properly, but I will explain to you what it means, what I'm talking about. How is it going with the vacuum controlling? So first, when you start the rotary operation process, for example, in kind of distillation, whatever, is it in the reactor or in the rotary operator, it doesn't really matter. You set a certain vacuum, and the vacuum pump starts to work, and it works continuously without stopping at all. And the vacuum controller detects that, okay, the vacuum, it measures the vacuum continuously, and once it sees that the vacuum reaches the, let's say, 75 millibars, for example, which was set on the vacuum control, it closes the valve. What is the problem with this kind of regulation? As we talked already, there is always a leak in the system. So, for example, if the pump sees that the vacuum, which was set to 75 millibars, the vacuum decreased, So for example, the pressure, let's say, got to 75.1 millibar, it has to open the valve again. And it opens the valve, the vacuum goes down to 75 millibars, and then it has to close the valve again. And in this case, it will open and close the valve every second. Why? Just because we always have a leak in the system. It is pretty obvious. So the problem in this case is that as soon as it opens and closes every second, it will break, I mean the valve will break very quickly. Because internally, as it has to be a chemical resistant one, it is made of PTFE. There's a certain PTFE belly, and just believe me, it will break very quickly. So what they offer, not only vacuum pump, what do the manufacturers offer to solve this problem? They set a certain figure which is called hysteresis, and it marks the delta P which we can have. So for example, let's say we set a delta P of let's say 5 millibars. So we set on the vacuum controller 75 millibars, and we set a delta P of 5 millibars. So when the vacuum reaches the 75 millibars, the valve closes. So controller says to the valve close. The valve closes, and it will open only when the pressure will reach 80 millibar, because we set delta P of 5 millibars. Clear? Perfect. So in this case, we will have this kind of hysteresis, which is not good. Why? Let's imagine we want to we check the figures, the tables, and we define that, for example, our substance boils at 75 millibars. Then it will boil only if we set on the controller 75 millibar. Then it will boil only when the system will reach 75 millibar. But as we already discussed, we always have a leak rate in the system. So when the system reached 75 millibar and the valve closes, then the vacuum starts to decrease. So you can see here on the picture, let's say what this point over here is the 75 millibars. Let's imagine that we reach 75 millibars, and then the vacuum, due to the leaks, starts to decrease. We have the boiling only here because our substance boils only at 75 millibars, right? So this is the problem. Why? Because it boils only here, and most of the time it will not boil at all, right? That's the problem. So we need to set a vacuum which would be lower than our boiling vacuum. Let's say we have a boiling vacuum of 75 millibar. Then we need to set a vacuum of, let's say, 70 millibar. And delta P of 5 millibar. So here now, this dotted line, that would be 75 millibar. Delta P is 5 millibar. So we have we reached 75 millibars, and although we said 70 millibar, we reached 75 millibar when our substance starts to boil, but we are going below in order to have the evaporation, which will continue longer than 1 second, right? So here again, here we have 75 millibar, here we will have 80, and here we have 70, right? So sorry, my mistake, I mentioned 5 millibar. We need to set a delta P of 10 millibar then, because we reaching 70 millibar, right? So we will, in this case, we will have the evaporation which goes from here to here, right? Because we have 75 millibar here, the substance boils, it will boil in this region. but it will still will not boil here. That is the problem, right? So roughly half of the time we are not evaporating. We are just waiting till the vacuum will reach 80 millibar, and then it will go down to 70 again, because the controller was programmed like this with a delta P that we set. There is another problem. Not only we are losing time, but we are also overboiling the substance, because we are going lower with the vacuum. So some of the solvents will not condense here due to a high vacuum. They will just fly into the vacuum pump, and they will collect here in the receiving flask on the outlet of the pump. When we're talking about the solvent, it can be pretty much okay. But if we're talking about the distillation, which occurs very often in the reactors, so when we're talking about the distillation of a certain product that we want to get off the system, then it is a problem, especially if the product is a sticky one, you know, or maybe a very expensive one, and so on. So we want to condense all our product in the receiving flask that is not on the outlet of the vacuum pump, but is in our system, right behind the reflux divider, for example. Okay, is that clear?
Yes.
Sure, I can explain it once again.
Yes, I got it. What you meant. I was just curious how you decide the condenser.
How I decide?
Yeah, to avoid any overboiling vapor. Try not to get any vapor to your vacuum pump.
I see. There is a rule of thumb which says that when we are distilling, the amount of the condensate that we have in the condenser should not reach the height of 2/3 of the condenser. So when we are distilling, we need to always take a look at the condenser and see that the amount of vapors that are condensing on the spiral of the condenser, in case we have a spiral condenser, the level of the condensate is at the height of 2/3 of the height of the spiral. In terms, I think that's a rule of thumb which I mentioned, but if I got your question rightly, you are asking about the surface of the condenser, right? Very good question. I personally don't know how to calculate that properly, but I always take the how to say that, the examples from Heidelf and from Buchi. Definitely they knew what surface we need. So I take a look at the surface of the rotary evaporator. I take a look at the performance of the rotary evaporator, and I say, okay, this is the surface that will be definitely okay. If I'm not mistaken, for a standard rotary evaporator, the standard surface is about 1,200 square centimeters. And in this case, we can have safe evaporating with a performance of about 1 liter of water per hour.
Okay.
Roughly like this. These figures are in the catalogs, so you can easily get them from there. I think I will, after our training, I will send you I will just cut it out from the catalog and send it to you via Skype. So for a big rotary evaporator, there are also, for 20-liter rotary evaporator, there are also some data, so you can see the performance that we can get, and that's how I define what is the surface that we need to have enough surface area to efficiently condense the vapors of the solvent or any substance you're distilling.
Okay.
Okay.
I'm sorry. Can I ask? You said the 2/3 is the height of the the spiral should be 2/3 from.
Yeah, we call it 2/3 should be loaded. They call it.
Okay.
So the level of when we start to boil, how to define that the condenser works properly? If we have the condensate we are on the height higher than 2/3 of the height of the spiral, then we overloading the condenser.
Now I got it. Okay. Yes,
And
yes,
in
yes.
this case, we either need to decrease the vacuum or to decrease the vacuum level. So to make it, let's say, not 75, but maybe 90 millibars, or we need to increase the cooling capacity of the machine that cools down the condenser. But we also need to keep in mind that even if we'll, with a small rotary evaporator, if we will even have the condenser with a cooling capacity of, I don't know, 100 kilowatts, it will not work at all because the surface is limited. This is the point for another training, which I did for our customers about the thermostatic equipment. Another very interesting topic, because there are a lot of tricks and interesting stuff when we're talking about thermostatic equipment. So most like with the vacuum, which we discussed already, most of the customers are not thinking about the performance at a certain vacuum, but they are thinking about the vacuum level. So and I mentioned already to you, explained to you why we need to choose the pump that will have a certain performance at the vacuum level that we are going to operate at. The same thing for the thermostatic equipment. When we're talking about the thermostatic equipment, most of the customers think that if we have a, let's say, thermostat that can go down to -50, then we will be able to get down to -50. No, you won't. You will never be able to go down to -50 because most of the thermostats have zero performance, zero cooling capacity at -50. So it means that it can cool down itself, but it will never be able to cool down your application. So when you're talking about choosing a proper thermostatic equipment, you need always to take a look at the cooling capacity of the thermostat at a temperature that you're going to work at. I don't know if you knew about that or maybe heard about that, because this is something, a pretty common thing. As well as, at this point, I'm pretty sure you know that when you're talking about the -50 in the thermostat, then you need to understand that you will never be able to get -50 in your reactor. You will, in best case, you will have -35 in your reactor because you will always need a delta T.
Yes, I think it's another complicated system that I have to study. It's really something that I need to study as well. There are
Okay,
lots of
so
like heat,
you
like
can easily offer this. You can easily offer this training, another training for your, for Shingo. I don't know who is thinking about the training about the reactors, but this is something I can easily do for you as well.
Yeah, sorry to stop you. I think yeah, please continue for the vacuum pump.
No problem.
Yes.
Always happy to share the knowledge. Okay, so we discussed the vacuum controlling by means of the valve. So, and I explained to you the disadvantage of this system. The advantage is that it is relatively cheap. The disadvantage, we have the problems, first of all, with the evaporating time. So it will last quite long. And another problem is that it will overboil at a certain moment. And that's why a certain amount of vapors will go into the pump, and that is bad. They call it the, how do they call it? Let me remember. The conversion rate, not a conversion. Forgot the definition. No, not the efficiency. The Okay, never mind. You got the idea. So that the amount of solvent that will be collected not in the in the receiver of the rotary evaporator, but not in the receiver of the on the outlet of the vacuum pump. So in this case, we will have some problem because we will have some condensate here and we will have some condensate in here. Now going to the another type of the vacuum controlling, which is the controlling of the drive speed. This is the most advanced type of the vacuum controlling system, and it operates in the following way. We set a vacuum of, let's say, 75 millibar. Let's imagine our substance boils at 75 millibars. We set the 75 millibar on the controller, and as soon as the vacuum gets closer to 75 millibar, controller says to the drive, please, I beg you, please decrease the rotation speed. And by decreasing the rotation speed, it decreases the performance. And when it gets to a 75 millibar, when everything starts to boil, your substance starts to boil, the vacuum pump will continue to run at a speed that will compensate the leak that we have in the system. You remember that we discussed that the leak rate in the beginning, and the idea of the compensation is that we already reached the 75 millibar. We do not need a higher vacuum. We need only to keep a vacuum at 75 millibars, but we always have a leak in the system, which is maybe, I don't know, doesn't really matter what kind of a leak rate. We have 10 milliliters per minute. And the pump will run at a speed, the drive will run at a speed that will allow the pump to compensate this 10 milliliters per minute leak rate. Clear? And by this kind of regulation, we have two important advantages. First of all, we have a straight vacuum level. Unlike here, we have this kind of teeth. Here we have a very smooth vacuum that keeps, because we are not, the pump works at a certain speed that will just compensate the leak rate. And another advantage that we have, the second advantage, is that we will always, unlike here, we will always have the condensation continuously, because we are always running at 75 millibars, right? Third advantage, that we will distill continuously at all time. Unlike here, we have these, times when we are not distilling, because the vacuum is higher than we need it. Oh, not the vacuum, the pressure is higher than we need it, right? And the fourth advantage is that we prolong the lifetime of the vacuum pump. Why? Because here, vacuum pump always run at a constant speed. It always runs. Here, by decreasing the speed of the drive, we extend the lifetime of the valve, of the drive, or of the vacuum, not this valve, but there are some valves inside the vacuum chamber. You remember that, right? Yeah, I'm talking about the membrane and these valves, this one and this, that are inside the vacuum chamber. Clear? Okay. And this is the very great advantage for this kind of controlling. Vacuum brand has this kind of speed controlled pump. They call it the Vario pumps. Welsh, they have also their own product lines for the speed controlled pumps. They call it the EcoFlex, because that stands for the, how to say that, the eco-friendly pump. Because it saves, energy, and because it runs at a lower speed, and so on and so forth. K&F also has, if I'm not mistaken, 2 models, but they are very expensive, and comparing to Vacuum brand and Welsh, and not as good as by VacuBrand or Welsh. So that's how we control the vacuum inside the vacuum pumps. Here we can see also the different controls. As I mentioned already, CVC 3000 was discontinued. They have now a CVC Pro controller with a touchscreen display. They also have a VNC2 controller. This is an interesting item, but this is the okay. Let me explain to you what it is. Let's say another type of the automated vacuum controller. Here we are controlling the valve which opens and closes. But there is another way of controlling the vacuum. We can control directly the vacuum pump by saying the controller can tell the pump switch on or switch off. And this is the very rough vacuum control system. So I personally do not recommend to use it. But for some simple applications like filtration, it can be used. And this controller, it is not shown here, but on the picture, but on the other side over here, it has an electrical inlet and outlet for the vacuum pump. So you are connecting the vacuum pump to the electricity, not directly, but through this vacuum controller. You can connect it here, and you have another wire which is connected to the plug, to the electrical system, to the socket, not to the plug, to the socket, right, on the wall. So you set a certain vacuum here on the controller, and as soon as the vacuum is reached, the controller just simply switches off the vacuum pump, right? You also have to set a hysteresis here, and it will work as well as just as this kind of vacuum controlling system. So it will have the same hysteresis and the same issues, but the problem with this kind of controller is that it is not as precise as the valve controlling system, because the pump cannot start to operate at maximum speed right from the beginning. It will always require a certain time to start. We are talking about, I don't know, seconds or even milliseconds maybe, depending on the type of the pump, but still we need some time. So that is why the vacuum controlling wouldn't be that precise. Plus, I think you should know that most of the electrical items are burned down when they are switched on, because we have the maximum load at the beginning when we're switching on the electrical unit. So there is a higher possibility to burn down the drive of the vacuum pump by using this kind of controller. Is that clear?
Yes.
Perfect. But it exists, I mean, this type of the controller, so worth mentioning. That's the backside of the CVC 3000, quite a similar thing with the CVC Pro. This is the explanation why we need the vacuum control in the lab. So we yeah, by the way, there is another interesting option in the controller, both for VacuBrand and for Welsh. They have a program that allows to automatically determine the boiling point. How does it work? Very, very useful option, which is integrated into the controller by default. So you do not need to pay extra for that. Actually, it works very simple. Let's imagine we do not know what is the vacuum that we need to reach to get our solvent boiling. And in most cases it is like this, because what we have the table data for the solvent are given only for the pure solvents. You never have a pure solvent. It makes no sense, to distill the pure solvent. You always have either a mixture of solvents, or you have a solvent with your substance, and so on and so forth. So although you set everything according to the table on the rotary evaporator, for example, the vacuum that we will need to distill your solvent may be either higher or lower depending on what you distill it from. So it would be perfect to have a system that will define the vacuum level by itself, the vacuum level that is required to start the distillation. So what you do basically is you have the rotary evaporator, you set the rotation speed, you set the bath temperature, and then let's have a vacuum system that will define the vacuum that is required. And Vacubrand and Welsh, they offer this kind of system. How does it work? Actually, I'm not sure if I have. No, I don't. Unfortunately, I don't have any slides for that, but I will explain it to you because I think it should be pretty simple. We have at the beginning of the process, the vacuum pump starts to work, and the controller always measures the pressure inside the system. So let's separate the vacuum process into steps. How does it work? Let's say for zero moment, yep, pump starts to work. It measures the pressure. It is atmospheric pressure. First second. After first second, it gets the second value of the vacuum inside the system. Let's say within 1 second, it went from 100 or 1000 millibars down to 950 millibars. Delta P is not zero. So the pump pumps out the gas. The controller understands that. After, let's say, second number 2, let's imagine it goes down to 900 millibars. Second number 3, 850 millibars, and so on and so forth. But when it reaches, let's imagine that your solvent, for example, starts to boil at 100 millibars. So when we get to this point, at the moment X, let's say, at the moment X minus 1, for example, at 10th second, we have 150 millibar, right? Then the pump pumps again. It measures the vacuum. It reaches the 100 millibar. Then, at 100 millibar, the solvent starts to boil. The pump pumps again. I mean, it continues to run, and the controller within 1 second measures the vacuum again. It expects, the controller, that the pressure will drop again, but it doesn't. Why? Because the solvent started to boil. It means that we are pumping out some gas, the air, if we're talking about the rotary evaporator, but the air immediately is replaced by the vapors of the solvent. So the pressure in the system continues to remain the same as the 1 second before. Clear?
I see. Okay.
So at the moment, let's say second 11 second, we have a pressure of 100 millibar, and at the second 12, we again have a pressure of 100 millibar. Why? Because the solvent started to evaporate, right? And the controller understands that because it sees that the delta P is 0, and it fixes then the vacuum. It tells the drive, please stop to rotate, or decrease the speed of the pump, or close the valve, depending on the type of the control of the vacuum controlling system that we have.
Very clever.
Did I explain it properly? Do you understand what I explained to you?
Yes, that's why they can detect the boiling point of the solvent.
Yeah, so that is how they define the pressure when the solvent starts to boil, and that is cool because you do not need any additional how to say that, you do not need to come to the system and check it. Either it started to boil, or maybe already overboiled, and so on and so forth. That is really great. So this is how they can control they can define I call it definition of the boiling point. So we already
usually equipped with the standard vacuum pump.
It is equipped with the pump in case the pump is equipped with a controller.
Okay, it's more like advanced model.
Yep. So just like here, you can see if we have the controller on the vacuum brand pump or on the Welsh pump, then it is already there. I mean, this kind of controlling system. But of course, if we do not have any controller, then like here with a manual regulated pump, then we do not have any possibility to define the boiling point.
Okay.
So once you see a pump with a controller, you, at least from Welsh and from vacuum brand, you can say that you can define the boiling point. And by the way, another good thing, let me see. You can also buy from both from vacuum brand and Welsh only the controller and the vacuum valve. And you can use your own vacuum pump. So the vacuum controlling system is, which I explained to you just a few seconds ago. The controlling process is done by the controller and the vacuum controlling system, like vacuum valve. So you have any other vacuum pump already in the lab, you do not need to buy a complete system. You can buy a vacuum valve. You just need to think of how you will install it on the system, and the vacuum controller.
Okay.
Boom, boom. Okay, so we've already discussed the field of application. This is just some models. So for the filtration and aspiration, you can have the ME2, ME2C. By the way, what does it mean? ME, we already discussed that. M stands for membrane. E, ion, one-stage pump. 2 is roughly the performance at maximum pressure. So this means that ME2 means that it is one-stage membrane pump with a performance of 2 cubic meters per hour. And C stands for the chemical resistance, because there are two types of the pump that both manufacturers manufacture. They are either chemical resistant ones or non-resistant ones. The difference is the design of the material of the membrane and the vacuum chamber. So for the membrane pumps, for the chemical resistant ones, you will have a membrane that's the kind of a sandwich, which is made of rubber, which is covered by PTFE, and the vacuum chamber inside is covered inside with a PTFE as well, to have the chemical resistance. And for the standard not chemical resistant ones, they have the chamber which is manufactured out of aluminium, and the membrane is made out of fluoro rubber, some kind of fluoro rubber. So you can easily use it for the filtration of the ethanol, any kind of alcohols, actually, for the filtration of water, but not for the chemical aggressive ones, like chloroform, or I don't know, maybe some vapors of the hydrochloric acid and so on. For NT stands for the new technology. They used to have kind of an old design ones like this, M2E. I'm not even sure if they still manufacture them. I think they discontinued and changed it to ME1. So now you will see that it has the NT, which stands for the new technology. So MD4C and T means that that's the membrane That's the 3-stage membrane pump with a performance of 4 cubic meters per hour, chemical resistant modification. So for the rotary evaporator are the models. That's the NT, the Vario station. Again, I explained that for the station with the speed control drive, and for the vacuum drying chambers, we have the more how to say, models with a higher performance. They also have some protection here, like protection from the dust, which is very important when we're talking about the vacuum drying oven, because you have some dust. Indeed, you will have some dust inside the vacuum drying chamber, because you are drying something up to solid. The same station but with the controller, and that's the explosion proof one. And here we have the models for the local vacuum net. So you can, I will explain it to you a bit later on, give you some quick description. Let's keep this one. So this is now about the oil sealed pumps. I would be happy to continue the presentation, but I need to interrupt now for I think about 30 minutes because we have a meeting with our director, online meeting.
Okay. Sorry.
Yeah, no problem. So if you are ready to continue today, I will be able to do it, I think, within 30 or 40 minutes. If no, we can continue next week. No problem. Just let me know.
Okay.
Think it
Yeah.
over and send me an email. Oh, an
Okay.
email, sorry. Send me, just write me over Skype, yeah. About
Yeah,
that.
maybe not today. It's already 8 p.m.
Oh,
And
I see. You have
I
6-hour
wish I
difference now. Uh-huh.
or maybe next time, okay?
Yeah, okay, no problem, of course.
So I will maybe talk